Good morning students, welcome to the class. Last day we have discussed about CMOS inverter and this is the voltage transfer characteristics of the CMOS inverter. We discussed about different capacitances, right. So, if you have any MOS, so you can expect all of them have some internal capacitance. This is, you can say, internal node capacitance. So, this is CGD. Similarly, CGS, between drain and bulk you will be having CDB. Similarly, between source and bulk, this is your body. Body is actually, for NMOS it is grounded. Okay. So many capacitances exist, and if you think why they exist, because we have a structure and they form a parasitic capacitance, right. This is our oxide and this is our gate. This is N plus diffusion and this is P plus substrate. So, we have the capacitances formed between two plate, something like that. Okay. So, these all are not real capacitance, these are called parasitic capacitance. Okay. So, for MOSFET they are in the order of few femtofarads or even less attofarad, but if we multiply these at very high frequencies, then their effect is significant and we can see the loss as the loss in the gain of the amplifier. So, that is why we are studying high frequency response. Now, we discussed little bit about CMOS circuit, right, CMOS logic gates. So, if you recall, this is a NAND gate. So, if NMOS is in series, it is something like that, right, and if PMOS is in series, this is something like that, right. So, if you remember that and if you understand the logic, can you tell me what is BC, relationship between A and BC? Okay. So, we will check that, okay. We will check that and we will try to derive that. This figure is, I think, two figures are not correct, okay. We have to check that this upper figure is not matching, all right. So, lower figure if we check with this, so it will be something like, okay. This figure should be complementary, this is not coming, okay. This is same. So, this is not proper, but for this NMOS the connection is like this, okay. So, we will try to make the complementary PMOS connections. So, this should be in parallel and this should come in series with this. So, it should be something like this A and then this should, so this should be A, this should be B and C and this should be your Y and this should be your these connections. Then this is Y is equal to, okay. So, we have also discussed little bit about what are the different capacitances and this is our gate capacitance, this is our diffusion capacitance, this is our overlap capacitance and this is our junction capacitance. So, if we neglect these capacitances, if we keep this open at low frequency, then we get our hybrid pi small signal model, right. What is our hybrid pi? This G, this is source, this is drain, gate to source open resistance, right, and here we have a, suppose this is your VGS. So, this is your GM VGS and one resistance R naught. So, this is your low frequency model. At low frequency these capacitance behave like, what is the impedance of a capacitance? 1 by j omega c. So, as c is very small, at very low frequency they offer a high impedance and they behave like an open circuit, but at large frequency model we can think of gate to source and gate to drain capacitance. Okay. And there are other capacitance like drain to bulk junction, but we can neglect because they are very small. So, if we roughly consider that, okay, my off capacitance during cutoff, you see between gate to body, what is my total capacitance? COX into the area W into L. So, this gate to channel, the gate to body is my COX WL. Now, when this turn on in linear region, triad region, this half is coming, as if we are assuming half is there in the drain side and half is there in the source side. So, you see CGS and CGT, they are equal in triad region and their values are just half of this, because total capacitance should be like that. Okay. And if you add overlap capacitance, 2 COV, because overlap is always existing, right, this much overlap is there. So, these 2 overlap capacitance will be always there. So, total cap should be this plus this. So, this in drain side 1 COV will be there, in source side 1 COV will be there. Now, in saturation what happens to your channel? Channel ends quite early, right. So, at drain side my CGD is 0 and total capacitance is COXWL. So, we are considering as if 2/3 portion is there in the source side. So, CGS at saturation is 2/3 WL COX, and during cutoff there is no channel existing. So, CGS and CGD are 0, total capacitance remain between gate and body. Okay. And this is my overlap capacitance. Generally this L overlap is very small, roughly 0.05 to 0.1 of L. Similarly, we have a source junction, right. So, if you think about a 3-dimensional figure, it will have some bottom plate capacitance and some side wall capacitance. This channel side no side wall capacitance, other 3 side we have 3. So, all of these capacitances they form up this total junction capacitance. Okay. So, this is called depletion layer capacitance or junction capacitance. So, it is a this is N, right, and this is my P and they are in reverse bias. So, this capacitance is just like a reverse cap of diode, right, reverse bias capacitance, because this PN junction is in a always in a, because this bulk is always sorted, no. Otherwise what will happen? In the bulk large current will flow and that is not wanted. We want current to flow between drain to source. Okay. So, this cap is just like a reverse cap of any diode. Okay. So, if we change this reverse bias voltage V source and V bulk, then this capacitance will also vary. Okay. We can control. So, just like the varactor diode. So, high frequency model that we just discussed, that we will consider the CGS and CGD, the CDB we can neglect. So, if we consider these capacitances, so now our current you see KCL is changing, right. This current through this capacitance will come. In previous case we opened this, right. So, our current was this branch and this branch. Now, extra current from input to output will come due to this CGD. Okay. So, if we try to find a frequency where this current gain is 1. So, in this model what we will do, we will add one input current source and we will sort the output and we will try to make output versus input current. So, this is known as the short circuit current gain. This is a gain, right. Output current by input current is current gain and output is sorted. So, this is short circuit current gain, right. As there is a capacitance, so there will be a, what is the impedance? J omega C. So, some frequency component will be there, right. Omega is equal to 2 pi f. So, we can get a frequency where this I 0 by I I is 1, right. We can, from this ratio I 0 by I I, we can find a frequency omega t. If we put this omega t is equal to inverse of this value Gm by Cgs plus Cd, inverse of this value, then what will happen? I 0 by I I, they will get cancelled out and will become 1. So, this is that frequency where my gain is unity. So, this is known as the unity gain frequency. So, why it is important? So that I can tell up to how much maximum frequency I can go. If I want to design an amplifier, it is not that this amplifier will work at even at higher frequency, right. So, there should be a limit. Who will tell me what is my limit? This Ft will define what will be my limit. Okay. So, if you do the KCL at this node, this is GMVGS is this current and S into CGD E into GMVGS, that is the current flowing through this cap, right. This is the Laplace. So, as this CGD is very small, we are neglecting this at this moment to make it easier, this calculation to make it easier. And similarly, this we are trying to find the what is the input current II. What is the input current? This is CGS and CGD, okay. They are in parallel connections. So, accordingly we will be having the voltage drop is current flowing into equivalent capacitance. Equivalent capacitance is CGS plus CGD. So, from this we can calculate I 0 by II. So, that is a important figure of merit. Why? So, from this we can tell that how much frequency we can use this amplifier, what is the limit of this frequency. Okay. If we even want to, then what will happen? Our gain will fall. Okay. At high frequency gain will fall. Same thing will happen for BJT. BJT will also have a high frequency model. Now, we are defining some base emitter capacitance and collector base capacitance. So, one is base emitter cap. So, similarly, we are also having this base, collector and emitter. No? So, as we define CGS and CGD, similarly, we will be have to define the capacitance at base and emitter junction and capacitance and base and collector junction. Okay. So, here one term tau f is defined. So, tau f is a device constant with the dimension of time. It is known as the forward base transit time and represent the average time a charge carrier spends in crossing the base. So, this tau, this is a time unit and it is the base transit time. So, whatever the carrier there in this base, the base width, it takes how much time to cover this base junction, that time is known as the tau f. Okay. So, if we multiply the IC with tau f, what we will get? We will get the total charge, right. Q is equal to I into T. So, Q, if we multiply this base transit time and if we multiply this with IC, we will get Qn, right. And what we know, the charge stored, now we are thinking like, okay, if this junction behaves like a capacitance, what will happen? If we have any capacitance, Q is equal to C into V. Okay. So, from there we are trying to calculate the C, what should be the equivalent capacitance. We know the base emitter junction voltage, that is VB, we know the Q. So, we are taking a derivative, this is a small capacitance, right, it is not a linear capacitance, we are trying to find a incremental capacitance, okay, delta of that. So, del Q by del VB is my CDE, okay, and we are just putting the value of Qn and it is coming as tau f into del IC by del VB. Now, del IC by del VB, we know there is another term GM, transconductance. So, C becomes tau f into GM. So, it becomes tau f into GM, and value of GM we also know IC by VT, that also we can use. Okay. Similarly, another terminology is there, that is base emitter junction capacitance. One is due to base transition, base transit time CDE, another is due to the junction. Okay. So, this is CJE, that is, suppose at the, when your voltage is 0, that time your junction capacitance is CJ0. Okay. So, CJE, your total capacitance is just roughly twice the 0 when your base emitter junction voltage is 0, that time what capacitance remains, you first calculate that coefficient is generally provided. So, you multiply that with 2, roughly you will get the junction capacitance. Okay. So, this parameter is given, so you multiply it with 2, you get the junction capacitance. So, if we add these two CDE and CJE, we will get the total base emitter junction capacitance. Next, we need to find the collector and base capacitance. So, previous two was component of collector base to emitter. Now, we have a component of collector to base. Okay. Now, collector to base is in which bias? Reverse biased for active region, right. So, whatever capacitance we will get, that will be the reverse bias depletion capacitance. Reverse bias, if you recall, we have a this kind of voltage for reverse capacitance, this kind of voltage. No? So, same thing we will be having C mu 0, C mu 0 is the at the 0 voltage capacitance, and it will depend on the reverse bias potential, and M is your whatever the power. Okay. So, C mu 0 is the value of C mu at 0 voltage, Cb is the magnitude of the collector base reverse bias voltage, and M is the grading coefficient, typically 0.2 or half. Okay. If it is half, it will be square root. So, this is just a depletion capacitance equation. Now, we will use them. So, this is our C mu. C mu means which capacitance? Collector to base. Another is C pi. C pi is base to emitter, right, and that is equal to CDE plus CJE. In case of MOS, what were our capacitance? CGS and CGD. So, you just think the terminology is same thing, right. In MOSFET it was CGS and CGD. In case of this is C pi and C mu. C pi means base to emitter, this means Okay. So, do not get confused by these terminologies, these are just terminologies, you just go by the meaning. Base to emitter, base emitter capacitance, that is termed as CPI. I can term it anything. Between base to collector, CBC, that is termed as C mu, that is it. Rest of the stuffs are same. We will be having the low frequency model, and now this Rx is extra. This Rx, this value is typically very small and you can neglect, few tens of ohm. Okay, so, you do not need to worry about Rx. So, if you neglect Rx, rest of the stuffs are you already know, right, R pi, GMV pi, R naught. Okay. So, this is the large signal, this high frequency hybrid model of the BJT. Now, again we will try to find out a frequency where my current gain is unity. Just like the MOSFET we did, we will do the same thing. What we will do? We will sort the output, we will try to find out a ratio of the output current by input current. So, output current by input current in hybrid parameter, its terminology is HFE. HFE is forward current gain, right. So, HFE is nothing but IC by IB. So, this is like a small signal beta, IC by IB is your beta, na? So, HFE is equivalent to beta current gain, right. So, this parameter is your small signal current gain. So, do not worry about what is FE, HFE is hybrid parameter, it means your current gain, short circuit current gain, IC by IB. So, similarly, if we try to find out this KCL at this node, at this node if we do the KCL, it is GM V pi minus S into mu into V pi. What is I? I is equal to V by impedance. What is your impedance? 1 by j omega c. If you inverse it, what will become? J omega c into V. So, that is okay. So, this is just a KCL in Laplace domain. You can convert this S, you put S is equal to j omega, you will convert it into frequency domain. So, do not worry about this all big terminologies. If you just do a KCL here, you can arrive to this. Okay. Similarly, we have to find out the input voltage, this voltage. So, if I want to find out the input voltage, what should I do? We should find the equivalent impedance, and whatever current we will multiply that, we will get the voltage. So, what is the equivalent impedance? R pi parallel C pi parallel C mu. This parallel this and this are in parallel, because capacitance is 1 by j omega c. So, this connections means parallel connection for capacitance, right. So, this is my impedance R pi parallel C pi parallel C mu, and if we multiply with base current, we will get the V pi. So, this is simple KCL, this is simple, then we will get this ratio. Now, we will try to this term is neglected, okay. This omega c mu, this term you can neglect. So, it will be simplified as Gm R pi by 1 plus S into C pi plus C mu into R pi. Now, Gm R pi is your beta, right, and similarly just like these previous cases, you can neglect this one and try to find out the frequency where the gain is 1. Okay. So, that will become omega t will become beta 0 into omega b. What is omega b? 1 by C pi plus C mu into R pi. So, this is the frequency where my current gain will come as unity. unity current gain in dB, it will be how much? 0 dB. So, this is our HFE, and the frequency where it is coming as a 0 dB is of my unity gain frequency, and this roll off is 20 dB per decade or minus 6 dB per octave. What is the meaning of octave? Twice frequency, not 8. Octave means frequency is twice and gain is falling by 6 dB. Decade means if my frequency increase by 10 times, gain will fall by 20 dB. Octave means if my frequency increase by twice, my gain will fall by 6 dB. Okay, they are equivalent, same thing, same slope. Now, if we plot this FT with different values of IC, you see what is the value of FT? FT depends on GM and GM depends on IC. So, we can say FT depends on IC, this is a function of IC. So, if I vary this IC, my FT will also vary. So, I am plotting FT by IC and I will try to find out a range where FT is constant, and I will try to use that value of IC. So, I want to maximize, suppose you want to design one amplifier and you want to use this amplifier for high frequency applications, right. If you suppose you are selling a product is usable up to 1 megahertz and one product that is usable up to 1 gigahertz, which one you will sell costly? High frequency, right, because you are putting effort to make it work up to that higher frequency. So, you will obviously try to get some money out of it, right. So, these high frequency applications generally you will be seeing that their value is more. Why? Because your design challenge is more, right. So, you see your mobile phone, your every processor, whenever you will want to go for higher specifications, cost will obviously go up. So, same way here, you want to design a amplifier that can go to the maximum frequency possible. So, what you should do? You should choose a suitable IC for the maximum possible FT. Why? Because if FT is maximum, your amplifier can work for higher frequency ranges. Beyond FT, what will happen? My current gain is falling. If current is falling, your amplification will be also falling, right. How you get your amplification? Because IC is beta times IB, so you are getting amplification. Now, if your gain is started to falling, it will not be as efficient. So, the pole we were getting, we discussed this also in previous cases also, this cutoff frequency, this is due to what? High frequency cutoff frequency due to which capacitances? Internal capacitances, because internal capacitances take effect at high frequency. If you have a coupling capacitance, its value is small or large? Coupling capacitance, large. They are generally in microfarad, right. They are generally in few microfarad or even higher, and you think of internal capacitance, their value is in which range? Femtofarad, right. So, if you take a inverse of a large, its frequency will be high or slow. This value is large, 1 by j omega c. So, its effect will be large or small in frequency? Small. So, it will give me my, this will be due to the coupling cap and this will be due to the internal cap, because its effect will be large. If you take 1 by 10 to the power minus 14, so what you get? So, equivalent frequency will be on the higher side. So, again this is my cutoff, this cutoff is happening due to this effective C pi and C mu, and this 3 dB cutoff frequency will be happen due to this internal capacitance and resistances, and this roll off is 20 dB per decade or 6 dB per octave. Octave means twice the frequency. Okay. So, you see this pole equation is 1 by 2 pi C in into R sig, this R sig generally this is, and this equivalent capacitance they will give you this cutoff frequency. Any cutoff frequency you can think of a equivalent R and equivalent C. Now, we will discuss a Miller's theorem. Have you heard this theorem before? No. Okay. So, suppose when we do two port network, suppose this is our gate, this is our source, this is our drain, right. So, input to output generally we do not have any connections, right. We are having something like this, okay, whatever. Now, the moment I am having some component here, my equation get complex, right. You can understand from this. I am having one extra part, right. So, input and output both voltages I have to consider. So, my equation, the moment I am connecting my input and output side, this is my input side, this is my output side. So, whenever there is an impedance and connected, my equation get complex, right. So, if we can somehow break that connecting bridge impedance, if we can realize this with an equivalent input impedance and output impedance, then this sorting of this input and output is, this internal connection of input output I can avoid, and my equations will be simplified. So, rather than connecting that, we should connect some equivalent cap or equivalent resistance. So, this Miller's theorem helps us to do that. Okay. So, what it is telling, if we have a bridging impedance, suppose I have a big circuit and in this big circuit this is a part, and this node 1 and node 2, in between them a impedance Z is existing, right. And because of this, what will happen, I have to consider both V1 minus V2 by Z, this should be my I, na. So, I have to consider V1 as well as V2, my equation get two variables. Previously I was having V2 is equal to something, V1 is equal to something. So, only one variable, it is easier to solve, is not it. So, what I will do, the Miller theorems is suggesting that I should break this into two parts like Z1 and Z2, one impedance at the input side and one impedance at the output side, so that I can neglect Z and I can draw Z1 and Z2, still the circuit will be equivalent. And suppose the relationship of V2 and V1 is like that, V2 is an amplified version of V1. Suppose in between them one amplification is there. So, V2 is equal to K V1. Okay. So, let me tell this again. So, this is a part of a bigger circuit and this V2 is equal to suppose 10 V1, K is equal to 10, something like that. Okay. And one impedance is there between node 1 and node 2. Now, what Miller's is telling? Miller's is telling a way to replace this Z with input impedance Z1 and output impedance Z2. Okay. Now, what happens? No bridging impedance. So, my equation gets simplified, and he has calculated these values and told us that Z1 should be Z by 1 minus K and Z2 should be Z by 1 minus 1 by K. Now, let us see how these values are coming, the proof of Miller's theorem. So, what we will try to do? We will try to find out the current I. What is current I? V1 by this, V1 minus V2 by Z, right. So, your I is equal to V1 minus V2 by Z. What is your V2? K V1. So, replace that V1 minus K V1 by Z. Take V1 common, 1 minus K by Z. So, this is your current. So, in second case what we are doing? We replace Z, we are drawing Z1 and Z2. Now, if these two circuits are equivalent, the current flowing through this should be also I. Previous case I current was flowing through this, and I have replaced this circuit with this circuit, and I am expecting that they should behave like same way. So, if they are behaving like same way, my current should be same, right. So, that is my first hint. So, what I will do now? I will try to find out what is I1 and equate it with I, and I will get the value of Z1. So, what is I1? V1 by Z1. You see why the beauty is there, because I have only V1 equation, no V2. So, equation will be simpler to solve. So, if it is V1 by Z1, so I will just equate it with the old value of I, and what I will get? I will get the value of Z. You can do this, it is a simple KCL, you just solve it, you will get this, you will arrive this. Only one equation is there, that V2 is equal to K V1, rest of the thing is just KCL. Similarly, I will try to find out I2. What is I2? V2 minus V2 by Z2, and I will equate this with this current, and I will get Z2 is equal to Z by 1 minus 1 by K. So, simple theorem, but it helps. For example, suppose you have a common source amplifier. What is your input? Gate. What is your output? Drain. Now, when we do the small signal analysis, no connection exists between input and output, right, high impedance. But in the moment you will try to design an amplifier for high frequency, this will come. So, you can use Miller's theorem and break this capacitance like this, and your equation will be simplified. This CGD you can break like this, input and output. So, no connection exists between input and output, your equation is not complex. Clear? So, this will come into the inside coupling cap, this will get plugged with the load cap, life is simple. Okay. So, application of Miller cap you will find for all high frequency model. Okay. So, we will conclude here and we will end today's class here.